Welcome to the next video in the course in real analysis. This is lesson 5, discussing ordered fields. In this video, we will define compatibility with addition and multiplication. We'll define what an ordered field is, positive and negative numbers. We'll give an example proof that in any ordered field, 0 precedes 1, and we'll see examples and non-examples and exercises at the end. So let's refresh what we have done so far. The field axioms told us about how plus and times work. The order axioms tell us about the less than or equal to symbol. From the concept of order, we could then use that to define concepts of bounds, maximum, supremum, and then all the corresponding things for the other end, the lower stuff. But we still don't have a sense of how plus and times interact with the less than or equal to symbol. And so that's what the concept of an ordered field is all about, is putting all of these things together and then giving a couple axioms of interaction, so to speak. First, we will define this notion of compatibility. So there is this notion of the compatibility of the pre-seq relation with plus, and then there is also a compatibility of pre-seq with times. So we say that pre-seq is compatible with plus if for any 3 field elements, if A pre-seqs B, then A plus C pre-seqs B plus C, effectively saying that you can add anything to both sides. That is compatibility with addition. For multiplication, we specify that that third element C has to be non-negative. Well, at least that's what we're going to call this eventually. Here I'm saying that 0 pre-seqs C, but eventually we'll understand that that is the same thing as saying that C is non-negative. So long as C is non-negative, then you can effectively multiply to both sides of the pre-seq relation. So with A pre-seq B, it follows that AC pre-seq BC. And finally, now that we've defined this notion of compatibility with plus and times, then let's suppose that we have some field which is also totally ordered by this pre-seq relation. If pre-seq is compatible with both plus and times, then we call the collection of all of these things an ordered field. So that's what an ordered field is it is something that is a field. It is also totally ordered, and the interaction between the ordering and plus and the interaction between the ordering and times are compatible. So let's give some quick, easy examples. If we take the set Q or R, right, the rational numbers or the real numbers, then this forms an ordered field. If we took the number set to be either the natural numbers or the integers, that would not be an ordered field because it would not be a field. Now, you might think, well, okay, so once you get past the integers to the rationals, you get an ordered field, and then when you move from there to the reals, you seem to continue to have an ordered field. Does it continue to be true for the complex numbers? Because we somewhat conceive of that as being the next construction after the real numbers. And it turns out the answer is no. And in fact, this is because there is no natural ordering on the complex numbers. Now, we did, I think, in a previous video, consider the ordering on the complex numbers given by the dictionary ordering. That was a total ordering. But it turns out that that ordering does not interact, it is not compatible with both plus and times. And in fact, no other ordering that you could possibly give that is a total ordering would ever be compatible with plus and times. The proof of this fact is a bit much for us, especially since this isn't quite the kind of thing that we're interested in this class, so I'm not going to go into the proof of it, but it is just worth remarking that there is no way to make C into an ordered field using the traditional interpretation of plus and times. Now, whenever we have an ordered field, we can define the notion of positive number and negative number. By the way, I think I've been throwing around the word number for a while now, and I should probably make it clear that I'm going to just call anything that is an element of a field a number, right? No matter what the field is, whether that is your traditional standard concept of what a number is or not, I just call anything like that a number. So here we'll talk about the positive numbers, that is to say the positive elements of my field. And so the positive numbers, which I'm denoting by this capital P, is just all the numbers such that 0 precedes x, right? Any x such that 0 precedes x. That is a positive number. And then the negative numbers are the numbers that precede 0. And there is just one number out of any field that is neither positive nor negative. It is the number 0. And finally, we define, and I probably should have bolded these, but the non-negative numbers are the positives together with 0. The non-positives are the negatives together with 0. Okay, let's do an example proof of a theorem. Let's show that in any ordered field, and so since we know that Q and R form an ordered field, then this proof will hold just as well for both Q and R. So assume for contradiction that this is not true. And we know, because we are dealing with a total order, that the assumption that 0 does not precede 1 is the same thing as 1 precedes 0. Okay, what are we going to do? Like, how are we going to get a contradiction? That looks very funny, right? Like, we know a contradiction must follow from this, but how? Well, we're going to have to use some kind of like notions of compatibility. In particular, it seems like we ought to be able to use compatibility with multiplication somehow. Because that's just one of there's compatibility with addition and there's compatibility with multiplication, and you wouldn't think that you could just arrive at a contradiction using only compatibility with addition. So you might have the instinct that somehow compatibility with multiplication has to be useful, I guess. But in any case, if we're going to do that, then, remember that compatibility with multiplication requires non-negative numbers. And we don't, right, that means we need something bigger than 0, not smaller than 0. So how about we take this thing and subtract 1 to both sides so that we get this. Now that move is justified by compatibility with addition, but now we have something that is 0 pre-seq -1, right? We have something that we can use with compatibility with multiplication. Okay, from here, what do we do? Well, why don't we just try, if we've got the number 0 around and we've got the number -1 around, then how about let's just see what we can do with those numbers, and maybe let's go ahead and multiply throughout this equation or this inequality by -1. Now, I guess I actually could write this more explicitly by saying that what I'm doing here is, by compatibility with multiplication, I am going to form 0 times -1 pre-seq -1 times -1. And the left-hand side, if we compute using what we know about fields, the left-hand side must be 0, because 0 times anything is 0, as we've already proved. And on the right-hand side, we know that -1 times -1 is 1, again, from what we proved using the field axioms. And so, and by the way, notice that I am multiplying the left-hand side by -1 and the right-hand side by -1, because when using compatibility with multiplication, you can multiply by something bigger than 0. And by assumption of this inequality, that's exactly what I'm doing. I'm multiplying both sides by something bigger than 0, namely -1. So anyway, so what we get, right, the sort of like end result of all of that is that we have now finally demonstrated that 0 pre-seq 1. Well, we now have two things using pre-seq. We've got that 1 pre-seq 0. We've also got that 0 pre-seq 1. By anti-symmetry, we can infer that 0 must equal 1, but it was a field axiom that 0, the additive identity, never equals 1, the multiplicative identity. So now we have a contradiction, and the proof by contradiction is complete. Okay, let's just introduce some exercises now. So as I was kind of definitely talking about a few minutes ago, let's consider the dictionary ordering on the complex numbers. And so I'm just going to remind you of what that was defined as. So if you take any two complex numbers, then here's what we're going to say is meant by this complex number being less than or equal to that complex number. It means that either the first one is smaller than the second one in their real component, or the real components are equal, but the first one is less than or equal to the second one in the imaginary component. So effectively, this is kind of like first sorting them by the real component, and if there's any ties, then we break ties by sorting them in the imaginary component. Your task for this exercise is to show that this does not make C an ordered field, right? So you are supposed to find some axiom such that this does not form an ordered field. Some axiom is violated. Okay, next we are going to show that if you take any ordered field, and that means that it is already equipped with some pre-seq relation, now we're going to show that if you, on the back of the definition of pre-seq, if you use the definition of precedence, that precedence is also compatible with plus and times in the following sense, right? So if I've told you what compatibility means when it comes to pre-seq, well, I haven't told you what compatibility means when it comes to precedence. It's very similar, but there is an ever so slight adjustment that we do have to make here. For plus, it's just a almost one-to-one reiteration. So there's nothing interesting going on there. This is just exactly what you would guess if you had to define compatibility with plus, given what you already know about compatibility with plus when it comes to pre-seq. But there is a slight difference when we talk about compatibility with multiplication. This time, we need to consider a C that is positive, right? Not just non-negative like we did with compatibility with multiplication in the pre-seq instance. Here, when we're talking about precedence, we'll take C is strictly positive. And then if A is strictly smaller than B, then AC is strictly smaller than BC, where when I say smaller, of course, I mean precedes. Okay, next exercise. Suppose that you have some ordered field. The number 2 is defined as 1 plus 1. Show that this chain of precedence is always satisfied. So in particular, you need to show that 1 precedes 2. You also need to show that 0 precedes 1/2, which is effectively to show that 1/2 is a positive number. And also you need to show that 1/2 precedes 1. Of course, 1/2 is nothing but notation for 2 to the negative 1, which itself is notation for the multiplicative inverse of 2. Okay, that's the first part of this exercise. Next, if you take any two field elements, we define their average as their sum over 2. Very intuitive. Now, what you are to show is that if A precedes B, then the average is in between, which is to say that that A precedes the average and the average precedes B. Or sorry, I said precedes, I should say precedes. Now, in this exercise, okay, we're going to have an ordered field yet again. We're also going to have a non-empty subset. And what we're going to investigate is how the notions of ordered field now start to interact with some of the notions of bounds, right? So we haven't really talked about bounds in this video at all, but we're going to start. And in particular, there is this very, very important equivalence between the notion of a supremum, which we could talk about in nothing but a poset, right? The notion of a supremum was fully defined in the setting of a poset. But here we're going to see that there is a different and very useful alternate characterization when you're in the context of an ordered field. So to get started on that, suppose that Y has a supremum, and let's call the supremum alpha. Show that the supremum has the following two properties. It is an upper bound on the set. That's actually a pretty trivial, very trivial property to show that the supremum has it. But then the second property is more interesting. It is the property that if you take this is not right. This should be strictly precedes. So if 0 strictly precedes epsilon, then alpha minus epsilon is not an upper bound. So that's a very important property of the supremum. And in fact, this goes in both directions, right? So we just saw that from supremum, you can infer these two properties of the supremum. But in fact, this also goes the other way around. If you have a number which satisfies these same two properties, right? Any number which satisfies these two properties must be the supremum. So it goes both directions, right? If it is the supremum, it has these two properties. If it has these two properties, it is the supremum. So that means that this is equivalent, right? These two properties are equivalent to the supremum. And in plenty of important settings, it's easier to use these two properties than it is to use the supremum. So this result we will use frequently in future videos. And I'd like to end the video with an invitation to ask questions. If anything here was confusing, or if anything in related parts of the textbook are confusing, feel free to leave a question in the comments below. Try to be as specific as you can. And if I can address it in the comments, then I may. But if it's substantial enough, then I might make a video and insert it into the playlist.